Hello friends. So let's talk about the analyzing full factorial design. So let's get started. The company run a full factorial design with 4 replicas to evaluate the pain adhesion resulting from 2 parameterized and 2 spray pressures. Now that the experiment has been run, so what can the process improvement team learn from the data? There are 4 steps we follow to evaluate the data. We'll start by fitting a full model to the data and reducing it approximately. After we select a final model, we'll use residual plots to check assumptions and look for potential outliers. Finally, we'll use the statistical model and graphs to select the process settings that will optimize the response. In the statistical software, factorial designs can be displayed in coded or uncoded units. We usually evaluate factorial models in coded units. For example, Minitab codes the low level of a factor to -1 and the high level of a factor to +1. This has a few benefits. One is that we can directly compare the size of the coefficients in the model we fit since they are now on the same scale. This allows us to determine which factor has the biggest impact on the response. Another benefit of coding factor levels is mathematical property of factorial designs we call the orthogonality. When a design is orthogonal, the effects are all independent of one another. This makes the analysis easy because any terms that are not significant can be removed at the same time when analyzing and reducing the model. When a design is analyzed in uncoded units, it may no longer be orthogonal. The full model for this experiment includes 2 main effects and 1 two-way interaction. A main effect is the effect of that factor alone averaged across the levels of the other factors in the model. An interaction between 2 factors occurs when the effect of one factor depends upon the presence of another factor. We'll rely on p-values to determine whether these effects that we see on the graphs are statistically significant. Here's ANOVA table for the full model. In the ANOVA chapter, we learned how to examine the p-value in the ANOVA table to determine whether a factor is statistically significant. Similarly, in a design experiment, we evaluate the p-value to determine whether the effects are significant. The null hypothesis for each term in the model is that the effect is equal to 0. In other words, there is not a significant difference in pain adhesion across low and high levels of the factor. We generally use an alpha value of 0.05 to determine whether an effect is significant. When the p-value is greater than alpha, we fail to reject the null hypothesis. When it is less than or equal to alpha, we reject the null hypothesis and claim statistical significance. Okay, for example here, output from the DOE. So which terms are significant in this model? In addition to ANOVA table, a Pareto chart of effects shows which terms contribute the most to the variability in the response. Here, the chart shows the standardized effect of each factor on adhesion. Any bar extending beyond the reference line at 5% significant level indicates that the effect is significant. The chart is a graphical way to view the results from the ANOVA table. Notice that the size of standardized effect is absolute value of T statistic from the table, with a reference line at the alpha level of 0.05, like the ANOVA table. The Pareto chart shows that both spray pressure and primer time significant affect paint adhesion. The interaction between the term A, B is also significant. All the terms in the model are significant at the 5% significance level, so no model reduction is necessary. The full model will be our final model. Minitab provides a model fit in both the coded and uncoded units. We can use the final model to predict paint adhesion. It will not always be the case that all terms are statistically significant. If the p-values for terms in the model are larger than 0.05, then we will remove those terms and refit the model. Before we use the model to determine the optimal factor settings, it is good practice to check the model assumptions using residual plots. We use a plot of the residuals versus run order to verify that the residuals are independent. If the data collection order affects the results, the residuals would not be scattered about 0, and we may see patterns in the points. Okay, so do the points appear to be randomly distributed and independent? You can see here there's no unusual patterns in the data, indicating that the errors are random and independent. The second assumption states that the errors follow a normal distribution. To test this assumption, we can use a normal probability plot. If the residuals follow a normal distribution, they should approximately follow the straight line on the plot. So do these points appear to follow a normal distribution? We can see here the residuals approximately follow a straight line, which means that the residuals are from a normal distributed population. The third assumption states that the variance or spread in the errors across all factor levels is constant. To check this assumption, we can plot the residuals versus the fitted values. The scatter of the points around the line should be similar across all factor levels, and no unusual patterns in the points should appear. So can we assume that the errors have constant variance across all factor levels? Now that we've fit a model to the data and check the assumptions, so let's use the model to understand the effects and determine which primer time and spray pressure will maximize the paint adhesion. The main effects for both primer time and spray pressure are statistically significant, and the interaction also significant with a p-value of 0.047. So we must evaluate the effect of the two factors jointly. In the interaction plot, the vertical the vertical axis is response pain adhesion. The solid line compares the effect of primer A at low and high spray pressures. The dashed line compares the effect of primer B at low and high spray pressure. So which of the following statements accurately describe the interaction between primer type and spray pressure? At high at higher spray pressure, we can expect higher pain adhesion. Primer A maximize pain adhesion with the low pressure, and primer B maximizes the adhesion with the high pressure. When using primer A, pain adhesion is similar at the low and high spray pressure, but with primer B, pain adhesion is significantly higher when it is sprayed at the low pressure. Or when using primer B, there is not a large difference in the pain adhesion with the low and high spray pressures. Okay, so do you have answer? Okay, so check the answer lesson at the next lesson. If we had to choose a primer type and spray pressure from the graph, which combination would we recommend to the paint company? We would choose a primer A spray at 300 kilopascals or primer B at 300 kilopascals, or A at 400 or B at 400. So what's your answer? Okay, so let's review. We fit our experimental data to a model and evaluated the significance of the terms. We re-verify assumptions about our data using residual plots. We made process decisions based on our analysis and graphical evaluation. Finally, we should also perform confirmation runs to verify results. Thank you for your listening. In the next lesson, we'll create a full factorial design using Minitab and JMP.